Hey class, today we're going to be talking about mechanisms, which is the last chapter of the structures chapter, last section of the structures chapter. It's pretty self-contained in itself, and there aren't that many mechanisms on our Artemis CubeSat kit, so that's why I saved it for last. So, mechanisms. The reason why we have mechanisms on spacecraft is because we typically need to deploy things, and the mechanism to deploy we call mechanisms. So you'll see here the difference between a stowed configuration and a deployed configuration on the left and on the right. The difference is that the mechanisms were at work between that transition. The mechanisms allowed for these different components to deploy and to be in its operational state. I like to think about mechanisms in the different dimensions that they work in. So in 1D, like a line, we have booms. In 2D, which is surfaces, we have solar panels or solar sails. And then 3D, we have habitation modules, and we even have antennae, which is something I forgot to put in the text here, but antennae are like dishes, so they exist in 3 dimensions. What you'll see here in the image is the Kepler configuration. Kepler is the Korea Pathfinder Lunar Orbiter. It's South Korea's first lunar mission. It was developed and managed by the Korea Aerospace Research Institute, KARI, and is scheduled to launch in July 2022 to orbit the moon for 1 year, carrying an array of South Korean experiments and 1 US-built instrument. Its launch vehicle is going to be the Falcon 9. The reason why we have to have stowed configurations is because of the volumetric limitations on rocket fairings. So let's just take a look at the difference between the stowed and the deployed. What you'll see here is that there's an antenna that needs to come up. I think that looks like it's right over there. You'll also see the solar panels in this configuration are collapsed into the spacecraft. But in this configuration, there are these, arms that come out and have the solar panels articulate toward the sun. Yeah, and that's everything obvious that last thing. There's this green boom that in stowed configuration is folded onto close to the wall and then deploys in this configuration. Okay. So let's see. Here is a really famous example. It's one of the most expensive missions we have going on right now, the James Webb Space Telescope. So this video shows how NASA's James Webb Space Telescope is designed to fold to a much smaller size in order to fit inside the Ariane 5 rocket for launch to space. The largest, most complex space observatory ever built must fold itself into a 17.8 foot or 5.4 meter payload fairing and survive the rigors of a rocket ride to orbit. After liftoff, the entire observatory will unfold in a carefully choreographed series of steps before beginning to make groundbreaking observations of the cosmos. So let's take a look at that. I know we've watched many videos of this already. But I liked this video because it shows the scale of the rocket and of the final spacecraft. Wow, neat. Okay, that's a CAD rendering, and here's the real thing. And then that's, who is this? This is Ariane Space's CAD rendering of the stowed spacecraft inside the rocket fairing. Okay, so let's talk about the specific mechanisms. Here is the boom. I'm starting out with the lowest dimensional mechanism. So I'll show you a video of how these booms are deployed. Essentially, they're wrapped up into a coil or a roll, and then they go through a specific like rolling out exit that shapes them into a more rigid structure. Yeah. And it's really cool how compact this entire system is. So that small thing can deploy 12 feet of structural, just structure. The cross section of the boom is this like teardrop. Yeah, there it is. Yeah. So maybe I could go through a little bit about what this like mechanism consists of. So A is a motor. B, those are the different booms. C, the steel strips, spools gear. D is the boom hubs or spools. E, where's E? E is down here. Encoder and power springs. F, top and bottom plate, holds it all together. G, radial arms. H, sliding rollers that help push it out. I, pin pusher and puller. J, launch lock bar. Anyway, yes, so many intricate little mechanisms to make this structure. Oh, and the question, if a telescoping boom gets damaged and is unable to retract, what is the procedure that most space engineers follow? Leave the boom extended, separate it from the spacecraft, attempt to fix it. So I would say that the reason why there's a mechanism in the first place is because there's some critical component associated with the mechanism. Aerospace engineers don't like to accumulate risk, and mechanisms are a very risky thing to put on a spacecraft. So we wouldn't put it on there unless it was absolutely critical for the spacecraft's function. So the first thing aerospace engineers would do if a mechanism is to not behave normally is to try and fix it. So for this boom situation, you can kind of like jerk the spacecraft or slew it really quickly to use your angular momentum to fling that boom outward. Maybe that's something you could do. But I mean, if you've tried as much as you can without really sacrificing a lot of your spacecraft resources, then you kind of just have to live with it. And then you adapt mission operations around just having like a broken mechanism. Okay, so this is, the booms were to extend. Here is the mechanism box that we saw in the last slide, and it ultimately was to deploy a sail. So those booms were struts that were supporting the ends of this sail, and now we're going to look at a specific sail. This is a different spacecraft, but the concept of a sail is demonstrated here. You'll see this is a familiar picture in the structural analysis slide set from last time, but these sails are folded in a very intricate origami pattern. They're made of typically very thin membranes like mylar, the MLI kind of material. And they can be deployed in many different ways. We saw on the last slide that you can attach them to a boom that extends outward, or let's look at this video. This is from, is it Planetary Resources? So yeah. This study seeks to look beyond the use of radiation pressure for thrust. Oh, okay. So here you'll see the same concept of the booms dragging the corners of the sail outward. And then along the boom, the sail will start to unfold. And there's all the surface area that needs to be tensioned so that it reaches its full surface area. Wow. All right, so while that's playing out, can you steer small spacecraft propelled in this way, or must the spacecraft always be traveling away from the sun? So that's a brilliant idea. And yes, you can steer small spacecraft as you would steer a sailboat with the wind. The same kind of principles can be applied. So I looked at a NASA study that was done in 2011. That said, here, I'll play this with no sound. This study seeks to look beyond the use of radiation pressure for thrust and to explore a means of solar navigation whereby a solar craft would be steered by use of radiation pressure. The idea is based on a recent discovery by the study team. They found that transparent refractive objects may settle into a position where they feel a force that is perpendicular to the incoming light direction. The transverse force is akin to the lift experienced by an airplane wing and other airfoils. Thus, they call it optical lift. Objects in their experiments simultaneously thrust forward. The combination of lift and thrust allows for the optical steering of optical wings. So yes, totally, that can happen. Solar panels. So now let's just look at some videos of solar panel deployment. This video answers this question: would it be possible to use folded solar panels on a CubeSat as well, or do solar panels still take up too much space? So happy to say it's possible. This is a test of EXA's DSA deployable solar panels. And I think there are many companies that have deployable solar panels now. And then let's look at the other side of the spectrum of size of spacecraft, the ISS deploying their solar panels, where there's this extendable boom that is pulling solar panels to their open configuration. That right there is a truss. Okay. Antennas. So that's another mechanism that, typically needs some kind of surface area and depth. So I have two concepts here. This is from SMAP, which you have probably heard of quite a bit now in this class. I love to use this spacecraft because it has this huge antenna that needs to be deployed. It has this boom that needs to be extended. And then the spacecraft also needs to spin up, so it's an interesting attitude control problem as well. Yeah, so I think that this mechanism is really interesting in that it's like it folds up into a cylinder and then it like radially expands while tensioning the antenna mesh. And did you see there was some string that was pulling the center? Yeah, and then to rotate this thing, there's a spin bearing right there that transfers angular momentum between that antenna and the main spacecraft body. Neat. Okay. And then this is a inflatable antenna. And I couldn't find a YouTube video. There's a Vimeo video. So I'm gonna open up this link. Okay, it's by a company called Freefall.
Data is the telecommunications sector is looking to space for a solution. Soon, sells advanced inflatable antenna system, which finally enables big data from CubeSats and other small, low-cost spacecraft. Freefall started in the stars with antenna technology based on research in high-frequency radio astronomy, the digital divide. The unique inflatable spherical reflector is compact and lightweight and provides a wide field of view for complete coverage. This novel approach allows for a dramatic increase in data rate with minimum mass, power, and complexity, which is critical to the space-based communication systems of the 5G world.
Yeah, I remember inflatable antennas being a hot topic when I was a grad student or an undergrad, and they've come a long way. I'm like pretty impressed. On the topic of inflatable habitats, there was an inflatable habitat that was installed on the ISS. It was manufactured by Bigelow Aerospace, and it was called BEAM, Bigelow Expandable Activity Module. Here are still frames of BEAM inflating, but I also have a video. So there are astronauts who are using this little command box to inflate BEAM. It's not terribly exciting. It's just like mission operators talking to the astronauts, making sure everything's okay. Long process. Yeah, it's not even like the astronauts could really see what was happening through this hatch anyway, but that's what it looked like from the outside. In this image from video provided by NASA astronaut Jeff Williams floats inside the Bigelow expandable module, Monday, June 6, 2016. The crew of the International Space Station entered the newly expanded pod Monday to collect air samples. As is customary, they wore goggles and cloth masks in case of floating debris. Williams says the room is pristine but cold. NASA wants to make sure that multi-layered beam, an experiment led by Bigelow Aerospace, can withstand wide temperature fluctuations, radiation, and debris impacts over time. It will remain at the orbiting lab for 2 years. Oh, can you not hear me now? Okay, we're good. Beam remains attached to the ISS to this day, used for storage and some additional testing. So conceptually, this is what the module looks like from the inside. There are some air tanks, and I think this was like a umbilical cord to the air tank so that the astronauts from this side of the hatch could inflate the module. This is what the view from the hatch looking towards the end of the module looks like. How are furnishings moved into the inflatable structures by astronauts after inflation? Are the habitats bare besides straps to hold down sleeping humans? Do astronauts try to hook onto things in the main craft to try and move things into the habitat? So I think that they just use the habitat for storage. Another question was, are the module walls thick enough to prevent the type of galactic cosmic radiation And from what I've read, it's not as effective as the other ISS modules, the aluminum frame ones. So that might be the reason why they're using it just for storage. It may not also have all the amenities that the ISS modules typically have. Okay, separation modules. Also, a subset of separation modules are ordnance or explosive bolts. I think this is a pretty good video of a rocket stage separating. So you'll see that upcoming here, this joint. And I can tell it was an explosive device because there was that flash. And then there's a lot of debris that is coming out of the joint right afterward. Whereas if it were a spring-loaded device like this one here, then all of their components would stay within the two spacecraft. This thing is called a light band. There are bolts attached. Of course, there are springs. The springs are compressed, and because they're compressed, they have some potential energy that can be transferred to the spacecraft as it's being deployed. So you can kind of imagine like a slingshot of sorts. So yeah, once this lock goes away, then there can be a little push that separates the two spacecraft. Cool. Spin bearings. Remember SMAP? So SMAP had spin bearings, but the essential concept is that there are two parts of the spacecraft that rotate with respect to each other, and that's usually over some spin bearing. Here's a cross-section of a spin bearing where there are bearings, things that allow rotational motion. There can be a motor to actually drive that rotational motion. And here is a spacecraft that actually has this mechanism here in the middle. And there's a picture of it actually built. This spacecraft is called the Global Precipitation Measurement Micro-Imager spacecraft. It's part of the GPM, or Global Precipitation Measurement constellation. And this spin mechanism assembly is required to maintain a constant spin rate of the instrument of 32 revolutions per minute for the 3-year mission, plus the duration of any mission extensions. Yeah. Another spin bearing like thing that uses motors, something called a scan platform. Scan platform is just what instrument people want to call the motor, but it's for engineers, it's just a motor with instruments attached to the end of it. The SCAN actuator motor, built by the Jet Propulsion Laboratory of Pasadena, California, is part of the Voyager 2 attitude control system. It was used to slew the sensors, or rotate them slowly, so that they stay focused on a target as the spacecraft passed by the planet Uranus. This is the motor right here. It's on display at the National Air and Space Museum. But this motor is a flight qualified spare used in laboratory simulations to resolve in-flight problems encountered by the Voyager spacecraft. Yeah, motors offer rotational motion. They control it, and they sometimes also measure it, like they have encoders inside the motor. Oh, and I answered all the questions. Cool. I'm done.